The continued fraction of a real number is this really cool expression that is of this form. The real number is equal to an integer plus 1 over an integer plus 1 over integer plus 1 over, etc. that keeps going, and it will keep going on forever if the real number that we started from is an irrational number. This expression is not just a curiosity, it actually has a very interesting property in that if you cut off the continued fraction at any given point, then what you get is a rational number that is a very good approximation, and in fact one of the best approximations, and that can be quantified in a way, of that real number. So for example, for pi, this is the continued fraction, and if I forget about all that part, then I get that pi is approximately 3, which it is, and if you forget about all that part but leave the 7 in the denominator, then you get that pi is 3 plus a seventh, which is 22 sevenths, Archimedes' approximation of pi. What about if I leave the 15 in, then that approximation is 3 plus this number, which is another approximation that is a very good approximation of pi that is not so well known as 22 over 7. How do we find the continued fraction expression for, let's say, a positive real number alpha? We want to write alpha as a plus 1 over b for some b, and this will be between 0 and 1, so that a has to be the floor of alpha. And now I can solve for b in this expression, and then b will be 1 over alpha minus its floor. And therefore, alpha is the floor plus 1 over some other real number, and now I can apply the same method to this new real number and continue the expression. What I get is a recursive formula where I start with alpha, let's say that's alpha 0, and a0 is the floor of alpha 0, and then I'm going to be able to compute the next alpha by taking 1 over alpha k minus its floor, and ak plus 1, the floor of this number I just computed. That's going to give me a sequence a0, a1, a2, a3 that makes up the continued fraction of alpha. Let's do this for pi. Set pi 0 to be pi, and a0 to be the floor of pi. From basic principles, you can prove that pi is between 3 and 4, so the floor is 3. Now, what is pi 1? That will be 1 over pi minus its floor. That's about 7, so the floor of pi 1 is 7, that's a1. For pi 2 is 1 over pi 1 minus 7, that's about 15, so a2 is 15, and then this number is about 1, so the third one is 1, etc. And those numbers correspond to the first coefficients in the continued fraction of pi.